Okay. So, all right. So we. It's funny. I came in here last time and I had like twice as many pages of notes as what I got through, and I was like, oh no, I'm only going to get through half of these. We're going to get behind in the course. And then I go check my folder of files, and it turns out that every semester it goes that way. I only get through like 3 of those things. So we're actually on track to get through stuff. So I feel pretty good about that. And today, at long last, we are going to do some calculations in quantum electrodynamics. So last time, in addition to sort of motivating some of the essential ingredients like the Vertex Factors and the Propagators, and how to draw diagrams, I also mentioned a couple of important sort of tools that I said we would see later, wave functions for spinors or for fermions and their antiparticles, and completeness relationships for spin sums and orthonormality conditions. And today is where we're going to see a lot of that stuff come into play. So without any further ado, here are the Feynman rules for QED. So quite a bit of this is going to be similar in language to the Feynman rules we laid out for the ABC theory. That's of course why we spent time on the ABC theory. But of course everything's going to be a lot bit more complex than it was in the ABC case. So, so first we have to draw a diagram for a process. And we kind of have already covered the rules for drawing diagrams. You have essentially one vertex for QED, and you're allowed to just put as many of those in as you want, as long as they have a photon and then a charged particle coming in and out of the vertex. And you just combine those until you actually match the in states to the out states for the process that you're considering. So I'm going to assume we roughly know how to do that. It's the labeling of the diagrams that becomes important. So we're going to label matter lines, and I'm going to start using the word matter versus gauge fields or photons for QED. So whenever I say matter, what I mean is the matter fermion. So it could be an electron, it could be a muon, it could be a tauon, it could even be a quark. And you label your matter lines with arrows to distinguish particle type. So we've already talked about this. So if we draw a line, a matter line, then we need to put an arrow on it because that indicates whether we're talking about a particle or an antiparticle. In this case, it would be a particle. In that case, it would be an antiparticle, because you always compare the arrow on the line to the flow of time. So you put lines on them to actually have an example here, and then you label momenta, and we're going to do this like we did before. For external, we're going to label incoming momenta with P's, outgoing momenta with P's. Or, sorry, this is what I actually mean to do. So remember, the momentum you label with an arrow next to the particle line. You don't put that arrow on the particle line because it would be confusing with the particle line, the particle arrows. For external momenta, we label it with P, and the external momenta always have to go forward in time. Okay? For internal momenta, we label it with a Q, and Q could go either way. It doesn't matter. Okay? And by the way, in all of this, if there was a photon, either internal or external, you also label photon momenta. So you would give this a P if this was an external photon. You could give it a Q if it was an internal photon. Yes?
Are there massive gauge fields?
Are there massive gauge fields?
Yeah.
Absolutely. For the weak interactions, there are massive gauge fields, and that was why we introduced the Higgs mechanism.
Right.
We're not going to have to deal with that for QED. We'll talk about that next week. One thing to go ahead and point out while I'm on the while I'm in this segment up here, I say you only have to label matter lines with arrows. And the reason for that is because for QED, matter has particle-antiparticle pairs, but the photon does not. It's its own antiparticle. So there's never a reason to put an arrow on the photon line, because there's no reason to say it's a photon or an antiphoton. They're the same thing. That will be different when we look at the other interactions, okay? So that is something that will change later. Okay, that is just getting started. Number 2. Can't spell each external line, and what I have in mind here are these lines, okay, and they can again be matter lines or photon lines if you have photons which are coming into or exiting from the process. Each external line gets a factor according to the following. And I'm going to draw a little picture here with all possible cases. So this is the process. So we've got some stuff that's going to connect this. I could have an incoming matter particle, I could have an incoming antiparticle, or I could have an incoming photon. I could have an outgoing particle, an outgoing antiparticle, or an outgoing photon. Okay? And it doesn't matter if this is an electron, a muon, or a tauon. What's important is that it's an incoming particle, incoming antiparticle, photon, etc. Okay? Everything on the left is incoming, everything on the right is outgoing because time goes. Okay? Whenever you are writing down the expression for M, anytime you have an incoming particle, you're going to write down a U. Now U is that same U we talked about last time. Okay? So this is a little bit of shorthand because it's going to get some extra labeling in time. Anytime you have an incoming antiparticle, you're going to write down a V bar, where bar is the adjoint of V. And when you have an incoming photon, you're going to write down a factor of epsilon sub mu. Okay? And then it probably doesn't take a big stride to guess that if you have an outgoing particle, you're going to write down a U bar, an outgoing antiparticle, you're going to write down a V, and an outgoing photon, you're going to write down an epsilon mu star. Okay? Now, now for each of these, since each of these is a particle coming into or out of the process, we would eventually label it with a momentum. And maybe that's P1, maybe that's P2, maybe that's P3. So your picture would look something like this. But the question is, what do you write down? And remember, each factor of U or V depends on momentum. So what we would do is we would just, as an argument, remind ourselves that, for example, the U here is going to be the U for the P1 momentum. At this point, it wouldn't be confusing because the U has 1, the V bar has 2, the photon has 3. But you could have like 2 or 3 particles coming in. So you would have a U for each of them. And you would need to keep straight which of those factors of U is for which particle. And we're labeling the particles partly by their momentum. Yeah.
Well, how do you know whether to use U, like U1 or U2 on the spin? Is that
you don't have to worry about that right now. I'm going to come to the little S thing in a few minutes.
Okay.
So for now, just write down. So you would write down U1 or U2 or U3, depending on how many particles you have coming into the process. And again, as with the ABC theory, I'm going to write down all these rules, and then we're going to look at some examples, and that'll help it make sense. Okay? All right. And bear in mind, you're writing these things down. You're not putting it on the picture. I don't care about the picture. This picture is to help you remember that when you see this line coming in your expression, you're going to write down a U. In this case, a U1. And in your expression, you're going to write a V bar 2. Okay? Now, as you're writing these things down, notice every U is what kind of quantity? What are these U's?
Spinors?
They are 4-component spinners. Okay? If you look back at the list that I gave you last time where we wrote down the wave functions for the matter, there was an amplitude, an exponential that told us about the momentum dependence, and then there was multiplying it a u or a v. And that's the spinner part. That's the 4-component spinner. So these factors are spinners, or adjoint spinners, and these factors are space-time vectors. Okay? So you can already see you're starting to write down complicated objects. And in fact, you might start getting a little anxious about, well, wait a minute, don't I have to be careful about order? I can't just write down my spinners in an arbitrary order. And so what I will say is, at the very end of this set of rules, I'm going to come back to how you address the order. So it's not as willy-nilly as just write this shit down in any order you want and we'll worry about it later. You're going to want to write it down in the right order the first time. But that'll be evident in a few minutes. Okay, so vertex factors. Every time you encounter a vertex in a diagram, you're going to write down a vertex factor, I, G, E, gamma, mu. Okay? Where again, we learned last time that GE is defined as the square root of 4 pi over h bar c times the fundamental electron charge. We're not really going to worry about, if you want to do a calculation and get a number, you might remember this, but just to keep it clean, we're just going to write GE, and then we could always go look up or compute the explicit value when we need it. Now, an important observation, which will actually be part of our sort of figuring out the order of things, this has a space-time index, a mu. Okay? And where else does a space-time index appear in what we're looking at? At least in terms of these lines.
The photon.
Yeah, by the photon. So one thing that we're going to have to keep track of is what index does this thing pair up with? And it's going to turn out that for every vertex, there's a photon. And so the mu associated with the vertex factor is also going to correspond to the mu associated with, for example, maybe the propagator or the external index of a photon. Okay, so we're going to have to keep track of these things. And again, I'll show you how to keep track of it all at kind of the end. Okay, so then we have propagators. And we've already covered these last time. So if I have electrons, positrons, I'm going to write down factors of I, gamma mu, Q mu, plus MC. And these are for internal, I should say. Q mu plus MC over Q squared minus M squared C squared. Okay. So we only write down propagator factors for the internal lines. The external lines are getting these factors. Okay. The internal lines are getting propagators. And of course they're internal, so their momentum would be labeled by a Q. That's why there's a Q in that expression. And then if you have an internal photon, as we mentioned last time, you're going to write down a minus I G mu nu over Q squared. Or sorry, over Q. Should be Q squared. I don't know why I have a 2 lower 2 in my notes. And we could just say this is eta. Sorry. I've been doing general relativity too recently. Okay? And if I revert and later write G, I actually mean eta, the metric of Minkowski space. Okay, so again, and I'm going to come back to the ordering in a few minutes, but notice this is a line for this is a propagator for an internal photon. That is a photon which is entirely inside of the process. That means that it has to be sort of capped by 2 vertices. So this is going to have some eta mu nu. But remember, each of these vertices are going to get a factor like this. And so to identify what index we put for these, we just pair them up with the indices we've chosen here. So here we might put gamma mu, and here we would put the gamma nu. Okay, so what I'm saying is, even before you really understand how this works, it probably wouldn't be smart to do that. You know, because your indices are not going to do what they need to do. Okay? So we can kind of see where there's going to be some sense to the structure just based on where indices are popping up. All right. Because remember, at the end of the day, when we calculate m, we should get a number. So that means all the indices have to be contracted at some point. Okay. So now we get to some more familiar things. Conserve momentum at all vertices. And we do it the same way we did it before. We use a 2 pi to the 4th, delta to the 4, p total in minus p total out, where that p total could include internal momenta q. You know, it's just for every vertex, you add up every single momentum coming in and subtract every momentum coming out. And then integrate over all internal momenta with a factor of d4q over 2 pi to the 4th. Okay, it's the same thing we did in the ABC theory. And then the good news is the last step is the same. You start evaluating all of those integrals that you can using the delta functions in hand. And eventually you're going to get down to where you have an overall 2 pi to the 4 delta 4 p external in minus p external out. So you erase that and multiply by I to get m. Okay, so it's the same final rule that we had for the case of the ABC theory. All right? Now, the ABC theory was a realistic theory. Secretly, the ABC theory was for spin zero particles, so it was Klein-Gordon. And one of the reasons why the ABC theory was so much simpler is you didn't have to tell me what was going on with the spin or the direction. All you had to know is that it was moving with some momentum. So none of these factors existed. These factors are only telling you what direction spins or polarizations are pointing. That's all they're doing. Since there's no spin or polarization in the ABC theory, you don't have these labels. Okay? Now, another simplification of the ABC theory is everything was bosonic. Here, we know that the matter are fermions. So one of the things I hope you learned in quantum mechanics is that when you have fermions, you have to anti-symmetrize things over the fermions. In particular, you have to anti-symmetrize multi-particle wave functions for multi-fermion states. Here, what we discover is that we have to anti-symmetrize between diagrams related to each other by switching. So remember, when you anti-symmetrize, you take, for example, if you've got a 2-particle state, if you have 2 fermions, you write down the sort of product wave function of this one times this one, but then you subtract what you get if you interchange the 2 fermions, and then put a 1/2. Okay? So anti-symmetrization for 2 things is usually basically a minus sign. Okay? If you have 3 things, then it's a little bit more complicated, but there's always, you interchange 2 things, 2 at a time. Well, here what we're going to do is we're going to consider diagrams. So we're going to take 2 diagrams and we're going to look at them and we're going to say, can I get this diagram from this diagram by swapping 2 fermion lines, 2 external fermion lines. So if we switch 2 incoming fermion lines, so that could be an electron or a positron. So if I have 2 electron lines, and then I switch them, and that gives me the next diagram, I anti-symmetrize between those diagrams. Okay. If they're not related by that, you just add them. Okay. 2 outgoing electron positron lines. Okay, so you can also look at the things coming out, and if you have 2 electrons coming out, and swapping them ends up giving you a different diagram that you drew, then you put a relative minus sign. And then here's where it gets weird. Or an incoming / outgoing electron with an outgoing / incoming positron. Okay? And I'm going to show you an explicit example of this anti-symmetrization, so it'll probably make more sense through the course of an example than it will in reading those words. Okay? But essentially, if we have two electrons coming in and I swap them, and then I discover that what I end up with is a different diagram, I anti-symmetrize those two diagrams. If I switch to electrons or positrons, when I say electrons or positrons, I mean two electrons or two positrons coming out, I anti-symmetrize. If I take an electron coming in and a positron coming out and swap them, which seems weird, but we'll see an example, and then that diagram gives me another diagram I've written down, I anti-symmetrize between those two. Okay, so to finish up is sort of our mnemonic for order. So how do we get the right order for writing this thing down? Okay, remember, order is important because we've got to make sure, principally, that since we're dealing with spinors and spin matrices, and we're not using index notation for those, since we're using matrix multiplication, we have to get the order right. For spacetime indices, it's not as important because we know index notation is never gonna, it doesn't care about the order you write things down. So here we go. To get the right order, we make, I know what you're all going to have for lunch tomorrow, spinner sandwiches. By following, or by starting with, by starting with outgoing matter lines, and tracking backwards to an incoming matter line. And you'll see what I mean by this in just a moment. But the idea is I would start, if this was connected with a diagram, to write down the expression for M, I would pick one of these two and I would go backwards until I came out here or here. And as I go backwards, I have a line, and then I have a vertex, and then I might have a propagator, and then I'll have a vertex, and I write things down in the order I encounter them. And if I do it in the order I encounter them, I'm guaranteed that the expression I write down is a scalar. It'll have the right matrix, row matrix, column matrix, square matrix order. And again, we'll see it in an example. Why don't I bother with the external photons doing that?
Because they're not spinners.
Because they're not spinners. You don't actually care where you write them down. You can kind of put them anywhere you want it. Okay? All right, so I know it's almost premature to ask if there are questions. Yeah, Spencer. But Spencer always has a question. So Spencer.
What are those superscripts on number 5? Delta function.
Those are Q's.
So this is, sorry, so here, yeah, let's be, so this is P/Q total N minus P/Q total L. Where what that means is it could be an external or an internal momentum, because at any vertex you might have some internal momentum coming in or out. You might have some external. Okay, so yeah, go ahead, Will.
So even with Rule 9, it feels like you'd still have some ability to like flip spinners around. Like if you have the case where you have a photon that spontaneously becomes an electron, anti-electron, and then recombines.
Let's just look at examples. Yeah, I know it doesn't really seem like it's going to work out, but just trust me, we'll look at some examples. There are a few cases where this is not going to suffice, and we'll talk about those in due time. But for most simple diagrams, this is going to be sufficient to get all of the things that we need in our expression. Okay, that means all the vertex factors, all the labels for external particles, and all of the propagators. Okay? So just by way of an example, to kind of flesh out how this works, let's talk about the process of electron scattering. Okay? So everybody take a moment and write down what you would think would be the lowest order diagram to electron scattering in QED. Okay, so just draw the diagram. So not using my cards, I gotta start using my cards again. Okay, so, Will, you're on deck. What does it look like?
Like, do we draw it?
Sure, come on and draw it.
Okay. I was gonna say, I'm gonna stripe it.
Draw a bunch of vertical lines.
So yeah, that's a good point. We have to draw a connected diagram, so, God, you do that so big. Yes, good job. I have to write down M's. So, sorry. Okay, so this is Will's diagram. Very nice, Will. Okay, all right. Okay, so Will was partly right. He's like the Tinker Toy guy. I got that right. But we remember we have to do some labeling. So we have electrons coming in. So these should be labeled with electron lines, and we have electrons coming out. And of course, now we see that Will was correct in writing down the vertices because we have a charged particle coming in, a charged particle coming out, and a photon attached to the vertex. Let's go ahead and label the momenta. And you can pick any labeling you want. I'm going to call this P1, P2, P3, and P4. And, I'll make that statement in a minute. Okay, and we don't really have to do it here because this is so simple. But in future problems, especially when they get really complicated and you have internal matter, it's useful to label what the particles actually are. So we could say this is an electron, 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 electron. Because for instance, this could be electron-muon scattering. And until you put the E in the mu, we don't know whether you're talking about an electron and a muon or an electron and an electron. Okay, so now we have the complete diagram. We're going to label that one internal momentum. I'm just going to call it Q. I'm not going to put a number on it because there's only one internal momentum Q. And we have all of our labeling down. Now we actually get to step 2. And here we go. With step 2, we're going to pick any external line. So I'll just start with this one. What factor do I write down for this external line? U bar what?
P3.
Yeah, U bar 3. Okay, you can write P3, but you're going to get tired of writing P's. So we write down a factor of U bar 3. And then following the line, we hit a vertex. So what do we write down? I, G, E, gamma, mu. Okay? And so there's probably a little modifier in here. We track backwards along matter lines. So what I mean by that is I don't want to come back and then hit this vertex and go through a photon. I want to stay with matter if I can. Okay? So that means once I come back, hit this vertex, I'm now coming out this line. So what factor do I write down for this guy? U1. It's an incoming particle with momentum P1. Okay? All right, look at the magic of what just happened. This is a column spinner. This is a matrix in spin space. And this is a row spinner. So just with the matrix multiplication, we have a number in spin space. Okay? All right. Now we're not done because that's not the only line to follow. We can also write down following the other matter line, and in that case, not wasting time, we have U bar 4. I want to put a different vertex label because this is a different vertex than this one, so I can just put I, G, E, gamma, nu. And then I leave on the incoming P2, so that's going to be a U2. Okay, again, it's got the right structure, row, matrix, column. And then, last but not least, what am I missing from my expression? In terms of lines. Yeah, I'm missing something for the photon, but that's an internal line, so we write down the photon propagator. So we're going to have a factor of minus I, eta, and now I can see I want to put the indices to be mu and nu over q squared. All right, so now I'm to this point. So I'm going to conserve momentum at all vertices with the appropriate factors. So I have P2 coming in, so going across the top, P2 coming in, Q coming in, P4 coming out. I'm going to have, for the lower vertex, P1 coming in, Q going out, and P3 going out. Okay? I have one internal momentum to integrate over. And then I just put the integral sign on that. Okay? And after our fun little heyday prior to spring break, you all should now be relatively comfortable. I mean, this is a complicated expression, but when you're evaluating the delta functions, it's the same game you played right before spring break. Okay? The only thing to keep in mind is that when you do a substitution for a momentum, you substitute these labels as well. Because 2, 4, 1, and 3, those are all labeling momentum. Okay? So without any further ado, I'm going to assume that you can evaluate this using one of these delta functions. You're going to get an overall delta function for the external momentum. Okay, that's this factor here. We're going to erase it and multiply by I. So let me just write down the final answer. And then I will take Kowalski's question.
No, it's okay. It's resolved.
That's sweet. And then I'm going to have minus I eta mu nu over P4 minus P2 squared. And all of that is going to be multiplied by I. Okay? Okay, so you might have noticed none of these, well, actually, sorry. Actually, I said something which ends up not being the case. It could have been the case, but it's not going to be the case. You actually will never find yourself futzing with the labels of the U's and the V's. And the reason for that is because those are always external momenta. When you're using the delta functions, you're always going to be getting rid of internal momenta. Okay, because you're integrating over internal momenta. So, here, since there's a Q, you would use one of these delta functions, actually this one, to replace the Q with P4 minus P2, but you're not replacing the external momenta with anything when you evaluate that delta function. Okay, so back up on what I said. All right, so questions about how that works for this simple example? None? I don't even know. Is this thing in the frame? Is it like, it came with the frame? Yeah, it's in there. Okay, all right. So now, we should ask ourselves, you guys can eat your pizza. I don't know why you're waiting.
Because now you're looking at me.
Now we're looking.
Hold on.
Just ridiculous. Open that all.
Eat. I don't want you to starve. That would be wrong and stuff. Okay. I think my tripod is now crooked. Okay. Anyway. All right. So sorry about that. Brief interruption. Our students are hungry. We clearly do not feed them as we should. Okay. So there they go. All right. So. In the program of doing Feynman calculations, we have to ask ourselves, is this the only diagram? Or perhaps more importantly, is this the only second order diagram? There's obviously always higher order diagrams. But is there another second order diagram that we could draw? And is there?
If you were to label Q differently, you would just get the same answer, right?
Yeah, so labeling Q being down is not going to change anything.
Right.
Yeah. So I wish it would, but it won't. Actually, I don't wish it would. It would make it harder.
Yeah.
Okay. So what could we possibly do to generate another diagram that's second order? Well, actually, let's not make it that complicated yet. We can just take these two lines and switch them. Okay, so let me draw the diagram. Let me draw it. So we start with exactly what we started with before, where again, this is P1, and this is this is P2, and this is P1, okay? I want to have up here P4 and P3, okay? And this is an important rule in writing down diagrams. One of the things you can do to sort of organize your diagrams is to first draw the external momenta labels. Because the one thing you don't want to do and confuse yourself is to draw a diagram where I have P1, P2, and then P3, P4, because it's not going to combine nicely with one where I have P3 and P4 in the opposite places, okay? So now what I can do is I can say, oh, well, I can let this P3 come from this vertex, and let the P4 come from this vertex, and that's a new diagram. And we talked about why this was new when we were doing the ABC.
Yeah.
For example, remember here the P4 momentum is determined by the P2 momentum and how much momentum is transferred by the photon. Whereas here the P4 momentum is determined by the P1 momentum and how much momentum is transferred by the photon. Okay, so these are kinematically very different diagrams. But now we have to ask ourselves, are they related by anything in step 8? And the answer is yes. They're related by taking two external fermions and swapping their order. So at the end of the day, if I call this amplitude M1 and I call the amplitude from this M2, then at second order, the total amplitude would be the difference. Okay, I'd have to put in a relative minus sign. All right?
How do you
Now-
know which one to subtract?
Say again?
How do you know which one to subtract?
It doesn't matter. You're going to square it anyway.
Okay.
But the fact that you're subtracting them is important. Okay? Okay, so interesting observation. If we were instead considering electron-muon scattering, this would not be allowed. Okay? Because if this were electron-muon scattering, this would be a muon. This would have to be a muon because a QED vertex has the same particle coming in as what comes out. So since this is the vertex, the mu coming in has to be the mu coming out, and this would then have to be an electron. But this is a different process than this because this is a muon coming out with P4, this is a muon coming out with P3. And those are different in and out configurations. Okay? But obviously if these are both electrons, I don't distinguish one electron from the other, so it really is just an interchange of the two outgoing electrons. And so I have to anti-symmetrize. Okay, so, yeah.
Does the Q arrow on the photon being pointing up mean anything?
No, yeah, so you could literally make this point down, go through the calculation, and you will end up with the exact same expression. So it's arbitrary. Of course, if you make it point down, it's going to change the sign here and the sign here. But the end of it will be the same. Okay? Yeah.
I think I just missed this step. How did we get rid of two delta functions within the one integral?
Okay, so we take one of the delta functions and we use it to evaluate this integral. So that means I can take this and set Q equal to P4 minus P2 everywhere I see Q. So for example, here I replace Q with P4 minus P2. Boom. Here I replace Q with P4 minus P2. But that just gives me delta function of P1 minus P4 plus P2 minus P3. But that's the thing that I erase in this step.
Oh, right, we just erased it.
Yeah, you just erased it. That's how you got rid of it. You just erased it. Okay? Yeah. Matt.
For M2 here, would we end up with the exact same expression, except maybe like...
I am not 100% sure, but it would be easy enough to probably not, actually.
I would just put the brackets of the U's and the...
No. It actually would be different because, right, this matter line would go U bar 4 vertex
Yeah.
U1.
Like the brackets on the U's would change, and then the momentum thing on the bottom would change.
Yeah, you could certainly write this down pretty quickly just by permuting the indices here. So you don't have to go back to the basics. But for now, I would probably do that until you feel really comfortable with it. Spencer.
So, just to understand this physically, you're saying that if I have 2 electrons that even scatter macroscopically, like we do this and like this,
Sure.
I can't tell whether or not it's scattering like this or scattering like
Well, the only observation you're making, remember, this is the way that quantum mechanics works. The only observation you're making is this. You are not allowed to ask about that. And since I can fill this in with this or this, they both contribute to this amplitude.
even if it's this big, like.
Even if it's that big, yeah. Because you're not doing the measurement. If you try to do the measurement there, then you're doing a different thing. If you try to look here, you're changing the outstates. And that changes the process and the calculation and its amplitude and everything. Yeah.
If we were to actually go through this and come up with a number for the cross section.
Oh, we're going to. We've got a lot.
Yeah.
We got a long way to go.
How far would you go out to, third order diagram?
Oh, get a good answer?
Yeah, if you're actually doing this for an experiment, how many orders of diagrams?
Oh Lord, I don't actually know how to how many orders these things have been calculated. It depends on the process. For some processes, you can't do second order. Like there's not even a second order diagram. You have to start at a higher order. I don't know. I would never even want to go beyond like fourth order would be painful. Like I wouldn't want to go beyond that. But I mean, people do it. You get really good agreement with just the first few terms for a variety of reasons. But I don't know. Like I'm sure you can Google it. Like how many orders in QED perturbation theory have been calculated for this process or that process? Because it's different for every process. So it's not like you do it to fifth order or sixth order for once and the sixth order. It's different for every single process you could imagine. And it's also different if you include muons and tauons, like higher mass particles. Those change the answer as well. Of course, those change the answer by factors, or those changes are suppressed compared to, say, things that only involve electrons, because remember, your propagators for virtual particles have a factor of mass in the denominator, and the tauon and the muon are really massive compared to the electron. So there's a whole bunch of different ways terms can get small, beyond just being higher order. Okay. All right, so I'm going to do one more example of drawing a diagram, and then we're going to move on to the next important step, which is evaluating the average and sum over spins. So, all right. Woo, thank you. Yes, that was my trick for the day. No applause. Just throw money, 10s and 20s. All right, and look, I want to. These are the points where I have to be honest to you. Honesty with Uncle Alex. This is not what got me excited about particle physics. Like calculating Feynman amplitudes is not like I didn't go to grad school to do this for a living. So I find this as tedious and at some level as uninspiring as you might be finding it right now. But I promise you that in the next few weeks, we're going to take this to a place which is really deep. For now, literally, if you are interested in doing particle experiment, these are the kinds of things you have to calculate. Sorry, that's your business, okay? That is not why I got into this. But it is a very important part of the story. Okay, so I'm going to do one more example of drawing a picture just to show you how subtle it can be, and then we're going to do some more calculations. And that picture is the picture for E plus E goes to E plus E. So electron-positron scattering. And we can immediately draw two diagrams. Okay, where here would be our electron coming in, here would be our positron, here would be our positron coming out, and our electron coming out, and of course that's the photon that's being exchanged. But then we could draw a second diagram that looks like this.
Where's the arrow backwards on the lower left?
Oh, sorry, I did. Yeah, no. Here?
Oh, that's right.
Yeah, that's the correct way.
Sorry.
That's okay. I make more mistakes more often than you guys ask silly questions, so I always err on the side of you being right. Matt, oh, this is going to be a silly question.
On number 1, are we allowed to flip the outgoing state? So are we allowed to?
I'm going to talk about that. So the answer to that is no. Because, sorry, we're going to talk about flipping in a minute, but the answer to that is no, because think about the kinematic consequences of flipping those. Like if I flip these two and draw the diagram, it literally looks identical. In particular, things you might say about the momentum here, they're going to be the same statements. So there's really no reason that flipping those is going to cause any sort of change. Okay, whereas with the example here, flipping the two external ones means that the momentum here is coming from a different vertex in the diagram than it did. Both these momentum are coming from the same vertex. Okay. All right. So the question now is, I have two diagrams at second order. If I'm at step 8, which is like here. So according to step 8, what do I need to think about? Are these related by interchange? Okay? Now, they're clearly, as Matt pointed out, they're clearly not really related by interchanging two things coming out or into this diagram. We could take two things in this diagram and interchange them. But if we take this thing coming out and this thing coming out, we're not allowed to interchange them, right? Because the anti-symmetrization rule says you've got to interchange two outgoing matter or two outgoing antimatter, not an outgoing matter with an outgoing antimatter. Okay, but what it does say is you can interchange an incoming matter with an outgoing antimatter. Okay, so let's just do that to this diagram, for example, and see what happens. So I'm going to grab, just for an example, this, and I'm going to interchange them. So what that means is the upper vertex I'm now going to draw like this, and the lower vertex I'm now going to draw like this. Okay? Does everybody understand what I just did? I took this line and I interchanged it with that line in the only way that I possibly can. Okay? But hopefully it doesn't take long to realize this is the same diagram as this.
Oh, yeah.
So by rule 8, if this was M1 and this was M2, I would anti-symmetrize. Wolfgang.
The arrows are different. In the diagram, the left side.
Yeah, so flipping these two doesn't really change anything. Okay, so if I flatten out the photon line, I can take the two external things and flip them, and that's not changing anything. That was our discussion with Matt. So literally, you're free to deform this into exactly this diagram without changing anything. The anti-symmetrization step, this exchange was a change. But these other, like moving these vertices around, that's not actually changing the diagram. Ariel.
When you did the exchange, you still kept your incoming line though. Are you supposed to make it your outgoing line now, or is this not possible?
Are you saying, so anything on the left is incoming.
Yeah.
I don't care about the arrow.
Yeah.
And anything on the right is outgoing.
Right.
So an outgoing line became an ingoing line. I didn't move this line here because I can't. I literally took an outgoing line and I made it an incoming line.
What?
But then you made it.
Right, I'm exchanging an outgoing matter with an incoming antimatter.
Oh, okay.
So the matter becomes antimatter, outgoing becomes ingoing.
Okay, but it's
Both of those things switch.
Isn't that which works? But they have to swap those vertices. So you have
Yeah, they had to swap the vertices. Okay? All right, so I don't want to get to, I mean, yes, if you're going to compute several diagrams and then you want to calculate the overall amplitude, these anti-symmetrization factors are important, but they're really part of, detailed calculations, and I want to, for the moment, get on to, first of all, how do you actually finish evaluating these things, which that includes a lot of technicalities. And then ultimately our goal is to take this to something actually deep. So, we figured out now how to get an expression for m, and just repeating the example that we've already worked out. It's just so that we have it to reference. So if I have P1, P3, P2, P4, this is an incoming electron, so I'm doing electron-electron scattering. Actually, let's make this electron-muon scattering so I don't have to worry about that second diagram, and I'll do Q up. Okay, then we already know from over there that the amplitude, after we've evaluated everything, after we've evaluated the delta function, or evaluated the integral with the delta function and then erased the overall momentum delta function, our amplitude is going to be something like this. And there's an overall factor of I. And now, coming back to, I think, Will's question very early on, we have to remember that the U's that we see here all secretly have a spin label. Okay? So, so what would we actually do with this? Well, first of all, we have 4 external particles. Okay? For each of those external particles, we could specify their spin state. And what I mean by that is we could specify U of momentum I to be alpha I U1 I plus beta I U2 I, where I just goes over the 4 particles in question. Okay, Ariel, shh, hear you all the way up here. Okay, so what am I saying? I'm saying that, say, for example, the U1. U1 is some superposition of the upspin state and the downspin state where it's got some set of expansion coefficients. So I would have to tell you the value of alpha and beta to specify the spin state. I could say it's spin up, or I could say it's spin down and make one of them 0, but in general I don't have to. And then I would have to do the same thing for U2, I'd have to do it for U3, and I'd have to do it for U4. Okay? Now I could do that, I could tell you exactly what I am putting into the experiment in terms of spin, and then I could tell you exactly what I'm looking for coming out in terms of spin, but that's not what we do in practice, as we mentioned last time. In practice, we send in unpolarized beams. We don't care about we don't fix the spin of what's going in. And when we measure what's coming out, we just measure everything coming out, whether it's spin up, spin down, spin, to the left. I don't know. We just measure it all. Okay? So what that means is that for practical calculations, we want to average over all the incoming spins. So in this case, that would be the spin for 2 and the spin for 1, and sum over the outgoing spins, so the spins for 3 and 4. And so what I want to do now is go through the details of how we do that averaging and summing. Okay? So So first of all, if you're going to average anything, what's the first step in averaging? Summing. So, whether you're summing or averaging, the first thing you have to do is sum. So let's first figure out how we do a sum. So what I'm going to do is just notice that the expression m is always going to have factors of the following form. There's going to be u bar of something, and I'm just going to call it A to give it a label. There's going to be a matrix in spin space in between. In this case, it happens to be IgE gamma mu. In other cases, it might be something more complicated, but it's always going to be a matrix in spin space, so I'm just going to call that gamma 1, where that's a matrix in spin space, okay? And then there's going to be a row spinner. And then there's other factors in M, okay? So we notice that this expression for M does in fact have these kinds of factors. It's got 2 of them, okay? Everybody see that? Okay, this is a spinner sandwich. And there could be other contributions, okay? Now, what we're actually interested in evaluating, of course, is not M, but ultimately M squared. So let's think about what M squared is going to contain. So M squared is going to contain, among other things, of course, this term. But it's also going to now contain the complex conjugate of this term. Times other things. Because we're taking the complex magnitude squared. We take it and multiply by its complex conjugate. Okay? Now, you might go, wait a minute, you put a gamma 2 there instead of a gamma 1. It turns out we kind of need to distinguish this from this because when squaring the amplitude, we might find ourselves having to square something like this. And when you square something like that, you don't want to multiply it by this. Because then you would think that you're simultaneously summing over all these mu's. When in reality, you would do something like this to square it. So this 2 is just reminding us that this is its own separate quantity, and then we're multiplying it by something here, and we shouldn't be doing something silly like summing over the indices that appear in both simultaneously. But otherwise, this gamma 1 and this gamma 2 will roughly have the same form. Okay? And now we're going to do that thing you all hate, where I just arbitrarily massage things for no seemingly good reason, and you're like, that was totally unmotivated, but trust me, at the end of the day, it's going to be worth it. Okay, so first of all, what kind of quantity in spin space is that thing in brackets? It's a scalar, okay? So as a scalar, as a number, it is its own transpose, right? So I might ask you, am I doing anything non-trivial by replacing star with dagger?
Here goes. No, that's fine.
No, it's fine, because all the dagger does is it adds a transpose to the complex conjugate, but the transpose doesn't matter because this is a scalar. Okay, so now we can do the transpose of each thing separately. That's where we get something magical, okay? So we do the transpose dance. Reverse the order of the 3 terms and transpose them individually. Okay? And then we're going to remind ourselves of the definition of the adjoint u bar. So if you look at your notes from last time, I wrote down the expression for u bar. And the expression for u bar is just u dagger gamma 0. So I'm transposing that whole thing. So u bar itself is u transpose gamma 0, and then I'm transposing u bar, so I transpose that whole thing. But now we can do the transpose dance on this guy. Transpose dance all around the Earth. So I'm going to have gamma 0 transpose, u a, and then transpose of transpose is nothing. Okay? And now I'm going to do one of those really annoying things, which is to say, hey, you know what? Why don't we just put 1 in here? Gamma 0 squared is 1. So I'm going to insert a gamma 0 squared there. I'm also going to remember, and I wrote gamma 0 down explicitly in our last lecture, gamma 0 in this convention is a real symmetric matrix, so it's equal to its transpose. So gamma 0 dagger, or sorry, it's equal to its Hermitian conjugate. So gamma 0 dagger is just gamma 0. And then I have U of A. Okay? So again, I'm using that gamma 0 squared is 1 and gamma 0 dagger is equal to gamma 0. And then lastly, what I'm going to do is I'm going to repackage this because now I have U dagger gamma 0, but that's just U bar. And now I'm going to take this quantity and I'm going to define that to be the bar of 2. So if I have a spin matrix and I bar it, that means Hermitian conjugate and then multiply by gamma 0 on each side. That's just a definition. Okay? And then that's all hitting UA. So at the end of the day, after all of that massaging, my expression becomes this. Yeah?
Is there a reason why you only needed one gamma 0 on the UV in order for it to become its adjoint?
Yeah, the adjoint of something is that.
Okay,
So I grabbed one gamma 0 and combined it with the U dagger to make U bar, and took the other gamma 0 and the gamma 0 there to form this gamma bar. Is that?
so gamma needs both?
Well, it doesn't need it. This is a definition.
Oh,
I'm just defining the bar of gamma at this point.
oh okay.
So later, if you need to know what is gamma bar, well, just take whatever your original gamma 2 was, dagger it, and then multiply it by gamma 0 on each side, and just treat it as a definition. Okay? All right. Anyone who was awake and paying attention in the last lecture should see something useful in here.
U bar, U bar.
Yeah, you see a U bar, UB, U bar B. Because one of the very useful things that we wrote down last time was the completeness relation, that if I sum over the spins with a combination of U bar, then I can replace this with gamma mu, P mu plus MC, okay? Where we're going to go ahead and adapt a piece of notation that is very common in the calculational literature. We're going to call this combination P slash. And the reason we do that is because Feynman loved Guns N' Roses. So this is going to be P slash plus MC. Okay? And so this we can now write as U bar A gamma 1 P B slash plus MC gamma bar 2 UA. Okay, where I have to be careful because that's where this is sum over the spins of sum over spins for B of M squared. Okay, this expression is not this expression. This expression comes after I've summed over the spins associated with this U bar. Okay? Now what I would like to do is also sum over the spins for the A's. But we see a problem, right? What do we see? Yeah, there's a whole bunch of non-trivial stuff in between them. I mean, this is non-trivial in spin space. I can't just take this and push it over here. Okay? But in order to use the completeness relationship, I have to have them right next door.
Take the trace.
Exactly. So here is a magical property. You're exactly right. So here is, well, no. We're not going to take the trace. We don't want to, well, no. The trace is relevant. That's what's cool. The trace is relevant, but we're not going to take the trace because there's nothing in the rules that say take the trace of M squared. We do want to sum over the spins, but we don't want to take the trace. But here's a really cool thing which I don't know if you've ever seen before with regards to matrices. But here is a result that you can actually prove to yourself for matrices. And that is, if I have a row matrix times a square matrix times a column matrix, that's a number, right? That is actually equal to the trace of the matrix times the column times the row.
Okay.
And you don't have to take my word for it. Write down some matrices, multiply them out, and do it.
Well, you can't, because you can't multiply a column.
Yeah, you can. You know how to do that. Trust me. Okay? All right. So what that means is that here, where I have a row times a matrix times a column, I can replace that with the trace of the matrix times the column times the row. And holy snap, look at what I have now got in my expression. Yeah, I've got U A, U bar A, okay? So now I can, this is again just the sum over B. Now I can do the sum over B and the sum over A of M squared, replacing the combination U bar here with another factor of P slash plus MC. So at the end of the day, this is going to become the trace of gamma 1 P slash B plus MC, gamma bar 2 P slash A plus MC. Where in principle, these M's could be different. They would have labels. But since everything here is electrons, these are all electron masses. Okay? All right, how are we feeling about that? Feel good? I feel good! All right, so I'm glad you feel good. I feel good. I feel good! It's Mario's world! All right, so no, I saw this crazy interview with James Brown. You should look it up sometime. It's the funniest thing I've ever seen. Wolfgang, I see you out of the corner of my eye. Hold on, baby. Hold on. All right, so what, Wolfgang? Oh no, it's Spencer. That's why it was so funny. You did the Wolfgang wave.
What kind of sums are you doing? Because there's the sum of S from the contraction of the U, but where do the B's come from?
So remember what I'm doing is I'm summing over the spins of the spin states for the spinners with the A, and then separately the spinners with the B. These are the same spinners. They just appear twice because I squared the expression. And so when I do the SB sum is when I replaced UB, U bar B with this expression. And when I did the sum over SA is when I replaced the U bar here with this expression. Okay? All right. So we're almost there. At this point, we now have a rule of thumb because we don't actually have to do this consciously every time. It's always going to work out the same way. So now I can just give you a rule of thumb. And the rule of thumb is going to be something like this. By the way, I should go ahead and point something very important about this expression out. There are no spinners in it. There are spin matrices, there's gammas, and there's factors of the identity if you need it, but there's no spinners. There's no U's. Okay? Or V's if you had V's in the expression. Okay? So the rule of thumb now is to impose the sum over spin states. For example, SASB, whenever we encounter it, we replace in our expression for M squared the factor U bar A gamma 1 UB quantity U bar A gamma 2 UA, or sorry, UB, star with the trace of gamma 1 P slash B plus MC gamma 2 bar P slash A plus MC. Okay, so we just, everywhere we would encounter a term like this, we just replace it like that, and then we say, boom, I've done the spin sums. So this replacement is doing the spin sums, which we have to do both for the incoming and the outgoing particles. Okay? For the outgoing particles, we of course then want to average over the spins. So at the end of the day, I can take this example for M here, and I can now write down the final expression for the spin sum and averaged M squared. So here we go. So M is given by that expression. And just to clean it up, because it'll make the substitutions easier, just to clean it up, let me write it as minus GE squared over P4 minus P2 squared. U bar 3 gamma mu U1, U bar 4 gamma nu, U2 eta mu nu. Okay? And then when I square it, and for the moment I'm literally just going to square it. Okay? So I'm going to have my GE to the 4th over P4 minus P2 to the 4th. And then I'm going to write down exactly what I have here. And then I'm going to write I'm going to copy it, but again, like I said before, I need to be careful in labeling space-time indices so I don't actually repeat things. And so when I copy this, I might label it like so. Gamma lambda U1, U bar for gamma alpha, U2, eta, lambda alpha, and then that whole thing will be complex conjugated. So right now, all I've done is squared it. Everybody on board? Okay. And then to do the spin summed version of this, what I'm going to do is I'm going to grab this term, okay, and this term, and I'm going to combine them and replace them with the trace of gamma mu P slash 1 plus MC gamma bar lambda P3 slash plus MC. And then I'm going to grab this term and this term, and I'm going to replace them by the trace of gamma nu P slash 2 plus MC gamma bar alpha P4 slash plus MC. Okay. So at the end of the day, the spin averaged and summed expression for this would be, okay, now for the outgoing we just do the sum, which we've already done. For the incoming, we want to sum over all the spin states, but then we want to average. Well, we have two incoming particles with two spin states each. So the average would be 1/4 times the sum over all spin states. So we just throw in a factor of 1/4. And then I just dump that factor here times this factor. Okay, and that would be my final expression for the spin sum and averaged M squared. And then I would have hanging out my eta mu nu and my eta lambda alpha. Okay, because this would still have a mu lambda, this would have a mu lambda, this would have a nu alpha, and those indices would have to be contracted at the end of the day. Okay, so now looking at this, and I'm not going to do anything else, we'll do the details next time. looking at this, you might say, well, we're not done, Flournoy, because I got to calculate this trace. Okay? But I want you to look really carefully at what you see. This is a trace of a gamma matrix. That's got a gamma matrix in it. P slash is gamma nu P nu. Okay? So that's a gamma matrix times a momentum. But the momentum is a scalar in spin space. So it can, like, if you just look at the first factor here, because the trace is distributive.
Yeah.
If you just look at the first factor, that's going to be the trace of some momentum times gamma mu, gamma nu. And then you're going to have some other things that come out of these other terms. Does that look familiar?
Yeah.
You worked out a whole set of trace identities for the gamma matrices in an earlier homework. And that's where those are going to come in handy. Okay? So the final step in evaluating all of these amplitudes is actually going to be explicitly writing these things down using all of those trace identities for the spin matrices. Okay? And we'll see some examples of that next time. That's it for today.